Hi everyone. We're going to talk about movement of gases and how gases are transported throughout the body. We're going to be talking about oxygen and carbon dioxide, and we're going to be referencing partial pressures and gradients and diffusion because of those gradients. So if you are still a little shaky with those topics, make sure to get those cleared up before watching this lecture, because we're going to go pretty deep into those topics in this chapter or in this lecture. So ask questions, rewatch those old lectures, reread that part of the chapter if you need to before we get going here. But as always, let's start with our not really attendance questions for the day. First, which portion of hemoglobin does oxygen bind? How many molecules of oxygen can one molecule of hemoglobin carry? What allows a protein to perform a specific job? And what is denaturation? Now, some of these may seem like they don't really fit in what we're talking about right now, but they are going to play a big role in today's lecture. So go ahead and try to answer those before listening to what the answers are. And let's look at hemoglobin first. Which portion of hemoglobin does oxygen bind? Well, it binds the heme group. Specifically, it binds to the iron in each of those heme groups. That's the non-protein portion of hemoglobin. How many molecules of oxygen can one molecule of hemoglobin carry? Well, there were 4 heme groups per hemoglobin, and each one could bind 1 oxygen molecule. So 1 hemoglobin molecule can carry 4 oxygens. And that's oxygen molecule, which is O2. That's the oxygen that we breathe. What allows a protein to perform a specific job? Well, with proteins, it is all about shape. The shape of a protein is what allows it to do a very specific job, and it can do that very specific job very well. And finally, what is denaturation? Denaturation is a breakdown in a protein shape. Think back to Chapter 2 in Bio 137. There were different levels of structure of a protein. There was that sequence of amino acids, the primary structure. And then based on that sequence, it folded up or coiled up into a secondary structure. And then those different secondary structure domains interacted with each other to produce a 3-dimensional shape, a tertiary structure. If any of those levels start to break down, that's denaturation. And the result is the protein will change shape. And if it changes shape, it loses the ability to do that specific job. It may develop an ability to do a different job at that point, but it's all about shape. And denaturation results in a change in that shape. Now here, we're going to talk about the factors that affect hemoglobin saturation. But first, we're going to look at hemoglobin again. Now, this is still from that early part of the semester when we were talking about red blood cells. And here's our hemoglobin molecule, the 2 alpha chains and the 2 beta chains, each which have a heme group with an iron atom right in the middle of it. And each of those iron atoms will bind an oxygen. And this curve right here, I do not expect you to know this curve, but I want to explain what it's showing to you. It's showing to you at the partial pressure, which is down here at the bottom, how much oxygen is attached. And we'll come back to this in a little bit, but I do want to show you at the lungs, inside the alveoli, partial pressure of oxygen is 100. And if we go up we see that hemoglobin is 100% saturated. So there are 4 oxygens that get put onto that hemoglobin when we get to the lungs. So we're going to come back and look at this in just a moment after we talk a little bit more about oxygen and hemoglobin. So now let's look at oxygen transport, how oxygen is carried around the body. Well, most oxygen in the blood is bound to hemoglobin. Now, some oxygen is dissolved in the plasma. Gases will dissolve in water. So some oxygen is dissolved in the plasma. But most oxygen binds to hemoglobin, specifically that heme group. And what we see up here at the top is the chemical equation for oxygen binding and unbinding. Now, I know most biology students don't care much for chemistry, but this, I'm going to make it pretty straightforward, so you're not really figuring out an equation. I just want you to understand what this equation is telling us. HB. So HB is how we write hemoglobin. And when hemoglobin is not carrying oxygen, it's called deoxyhemoglobin. And deoxyhemoglobin is written HHB. So HHB, deoxyhemoglobin, is not carrying oxygen. But if an oxygen comes along, they can combine. And then the hemoglobin is carrying the oxygen. That creates something called oxyhemoglobin. And oxyhemoglobin is written HbO2. Hb for hemoglobin and the oxygen that it is carrying. But deoxyhemoglobin, remember HHB? H, remember, was hydrogen. When oxygen is attached to hemoglobin, it knocks that hydrogen off. And that's not really true, which we will see later. But for now, we can think of it as that. Oxygen binds to hemoglobin, the hydrogen ion falls off. So we have oxyhemoglobin and a hydrogen ion. But remember what the double-headed arrow means? That means that this can go in both directions. So if H plus attaches to hemoglobin, then the oxygen falls off, and we get deoxyhemoglobin and oxygen. So this can go both ways, just depending on if there is more H plus or if there is more O2. If H plus is low and O2 is high, then more oxygen is going to bind to the hemoglobin, and we will have a few H pluses left over. But if oxygen is low and H plus is high, then more H plus is going to bind to the hemoglobin, and then we'll have some oxygen available. So this goes both directions, just depending on if there's more oxygen or more H plus. Now that's going to play a key role here in just a little bit. In your head, be thinking about what does it mean if there is a lot of H plus. If H plus is high, what does that mean? So be thinking about that and we'll come back to it. Now we're going to look at a word, saturation. And saturation in general just means how much of something is something else carrying. If you saturate a towel, typically that means that that towel is soaking wet and cannot hold any more water. But in Bio 139, saturation is going to mean one very specific thing. When we say saturation, we mean how much oxygen is 1 molecule of hemoglobin carrying? I'm going to say that again. Saturation in this class will always mean how much oxygen is 1 molecule of hemoglobin carrying. Now, we might start talking about carbon dioxide, and we might start talking about pH, and we might start talking about various things. And when we say saturation, regardless of what else we're talking about, saturation means how much oxygen is hemoglobin carrying. So, even if you don't see the word oxygen, it's talking about oxygen. Now let's apply that to hemoglobin, which we see over here again, same picture that we saw on the previous slide. Hemoglobin can carry 4 oxygens. When hemoglobin is carrying 4 oxygens, we say it is 100% saturated. When hemoglobin is carrying 4 oxygens, it's carrying the maximum amount of oxygens. It cannot hold more than that. So it is 100% saturated. Saturated with what? Well, in this class, we always mean oxygen. Now, if one of those oxygens were to be removed and we had 3 oxygens attached, then we say that the hemoglobin is 75% saturated. If 2 oxygens are attached, then it is 50% saturated. If 1 oxygen is attached, it's 25% saturated. And if 0 oxygens are attached, it is 0% saturated. So saturation tells us how many oxygens are attached. If I tell you at some place in the body, hemoglobin is 100% saturated, what I'm telling you is at that place, the hemoglobin is carrying 4 O2s. Now, sometimes we may see a value like 96% saturated, and that doesn't fit here. What that tells us is most of the hemoglobin has 4 oxygens attached to it. Most of the hemoglobin has 4 oxygens attached to it, but some of them have less. On average, the hemoglobin is 96% saturated, is what that means. But let's start from the bottom and go up and look at a unique thing that happens with hemoglobin. And while it is unique to hemoglobin, it is something similar to what happens to all proteins. If you had me for Bio 137, you likely heard me say many times that anytime we add something to or take something away from a protein, it changes shape. We talked about this in muscles pretty deep when we added calcium to troponin. It changed shape. And that whole cross-bridge cycle was the result of adding something to and taking something away from a protein, causing it to change shape. Well, hemoglobin is a protein. So let's look at what happens when hemoglobin is 0% saturated. Well, it's going to have a certain shape. But when we add 1 oxygen to it, because remember, hemoglobin really likes oxygen. So if we are 0% saturated and an oxygen is nearby, then that oxygen is likely to bind hemoglobin because they like each other a lot. But the cool thing about hemoglobin is when that first oxygen binds, we've added something to the hemoglobin, so what's it going to do? It's going to change shape. And when it changes shape, in this new shape, it likes oxygen more than it did before. So it makes it easier for a second oxygen to attach. What happens when we add an oxygen? It changes shape. And it changes shape to produce a new shape that likes oxygen even more, making it easier for a third oxygen to attach. And when that third oxygen attaches, it changes shape again, and now it likes oxygen most of all, making the fourth oxygen easier to attach. The binding of oxygen causes a shape change in hemoglobin. And every time we add an oxygen, that shape change makes hemoglobin like oxygen even more, so that the next oxygen is even easier to bind. Now let's talk about some different factors that influence saturation. All right, now for this, I'm going to use the whiteboard. There are 4 factors that influence hemoglobin saturation. So let's make a chart here. On one side, we're going to put the factor, and on the other side, we're going to put the effect on saturation. Saturation with what? With oxygen. So first, the first factor is the partial pressure of oxygen. When the partial pressure of oxygen is up, that just means when there's more oxygen, what's that going to do to saturation? It's going to increase it. That one, I think, is pretty self-explanatory. If there's more oxygen available, then more oxygen can bind hemoglobin. When PO2 is up, saturation is up. Now let's look at PCO2, the partial pressure of carbon dioxide. When the partial pressure of carbon dioxide is up, saturation goes down. Because even though it seems like oxygen should have preferential treatment with hemoglobin, it doesn't. Carbon dioxide will bind to hemoglobin easier than oxygen will. So the more carbon dioxide is available, it will outcompete oxygen. Carbon dioxide will bind to hemoglobin and knock the oxygen off. So the more CO2 there is, the lower the saturation will be. Next, pH. Earlier I asked you, what did it mean when H plus went up? Well, hopefully everyone remembers, pH is a measurement of H plus concentration. H plus is a proton. It's the hydrogen ion. When there are more hydrogen ions, when H plus is up, pH goes down. The more H plus there is, the lower the pH. And when pH goes down, saturation goes down. So let's explain this a couple of different ways. First, we saw previously on that slide that H plus, if there was more of it, it would bind to hemoglobin, knocking the oxygen off. Well, that's what we see right here. When there's more H plus, when pH is down, the H plus will bind to the hemoglobin, knocking the oxygen off, lowering saturation. But let's talk about it another way. Think back to proteins. Think back to denaturation. Low pH causes denaturation. Low pH, acidity, denatures protein. The lower the pH, the greater the shape change. And if a shape change results in a protein, what happens? It can't do its original job as well. Now, similarly, high temperature also denatures protein. So when temperature goes up, saturation goes down. Temperature up, protein denatures, and now the hemoglobin can't carry oxygen as well. Now, temperature and pH, they kind of go hand in hand. High temperature and low pH both denature protein. When you put, let's say, a piece of fish in the oven, well, that fish is mostly muscle, it's mostly protein. And that high heat denatures the protein. That's what's happening when it cooks. When it comes out of the oven, it looks different, it feels different, because its protein was denatured. Now, I always ask in person if I have any people with a cooking background, because something else that you can do that a lot of chefs know is with fish, you can soak it in lemon juice or lime juice, something very acidic. And if you let it sit, that protein denatures. And even though you didn't put it in the oven, it gets cooked and it's perfectly safe to eat. It looks like a piece of cooked fish. It feels like a piece of cooked fish because the low pH has the same effect as high temperature. But tying that to hemoglobin, low pH and high temperature both denature it and reduce saturation. Now, let's look at a couple of real-world examples to put this at play. Let's first look at the effect, what happens in the body when you are exercising. Let's say you run across campus. And when you're running across campus, let's specifically look at your leg muscles. When you are using your leg muscles a lot, they're going to be contracting and relaxing, and they're going to need to make ATP. So they're using up oxygen. And when you're running across campus and your leg muscles are using up oxygen, the oxygen in your leg muscles goes down. And as they are making ATP and that oxygen is going down, they're producing waste, carbon dioxide. So the PCO2 in those leg muscles goes up. Now, back when we were talking about the heart, we mentioned something that happens when muscle is working faster than oxygen is being replaced. What builds up in muscle when it's working? Lactic acid. And lactic acid, as its name suggests, is an acid. So in leg muscle that's working, the pH drops as lactic acid builds up. And if you've ever felt your muscles after a workout, what do they feel like? They feel very warm. So the temperature in that leg muscle would be elevated. In muscle that's being very metabolically active, the PO2 is low, the PCO2 is high, the pH is low, and the temperature is high. Look closely and see if you can tell what they all four have in common. Well, low PO2 will have low saturation. High PCO2, low saturation. Low pH, low saturation. High temperature, low saturation. So this metabolically active tissue in your legs All four things that happen lower the saturation. And remember, when we say saturation, we're talking about how much oxygen is attached to the hemoglobin. And at first, this might not make sense. Why would we want low saturation where the body needs it the most? This leg muscle really needs some oxygen. Why would we want low saturation? Well, that's exactly what we want. Because if saturation is high, it means that hemoglobin is holding on to the oxygen. We don't want that. We want that oxygen to fall off of the hemoglobin so that it can diffuse into the muscle tissue so that it can be used. What that means is metabolically active tissue like muscle that's been working out creates an environment that makes it really easy for the oxygen to move from the hemoglobin into the tissue. All four of those factors reduce saturation to make it easier for the oxygen to move into the tissue. Now let's look, I'm going to change ink colors here. Let's look at what happens in the lungs. In the lungs, there's a lot of oxygen, so the PO2 is high. And in the lungs, the PCO2 is very low because we keep breathing it out. Inside the lungs is slightly alkaline, so the pH is high. And inside the lungs, remember, is outside the body. It's actually a little bit lower than the rest of our body temperature. And if you look at all those blue arrows that show what's happening in the lungs, what do they all have in common? They all cause increased saturation, which is exactly what we want to happen when we bring blood to the lungs. The lungs create an environment that make hemoglobin really, really like oxygen. When that blood gets to the lungs, all four of those factors help create an environment that makes it efficient to load oxygen onto that hemoglobin. So there's our high metabolism example, what's happening in the exercising leg muscle. We also talked about the lungs, what's happening in the lungs. And that's all oxygen in the attached to hemoglobin. But remember, some oxygen does dissolve in the plasma. Not very much, but some does. So let's talk about some disorders related to oxygen, and we'll talk about hypoxia. Hypoxia just means low oxygen. And there are different types of hypoxia. So let's talk about some of them. The first, anemic hypoxia. Well, remember back when we were talking about erythrocytes? When we talked about things that interfere with an erythrocyte's ability to carry oxygen, that was anemia. Well, the condition that results from anemia is anemic hypoxia. You can't carry oxygen as well because you have some type of anemia. Next, ischemic hypoxia. Ischemia is reduced blood flow. Ischemia is reduced blood flow. And if you're not able to circulate your blood adequately, then it's going to interfere with the ability to deliver oxygen. So that causes ischemic hypoxia. Histotoxic hypoxia. Histo means tissue, toxic means poisoning. So some poisons affect the tissue's ability to use oxygen. If the tissue can't use oxygen, that results in histotoxic hypoxia. The oxygen is delivered just fine, but the tissue can't do anything with it. This is how cyanide poisoning works. Cyanide is, when you hear people say, apple seeds, if you eat them, they will kill you. Well, apple seeds do have cyanide, but you would have to practically eat your weight in apple seeds to get enough cyanide to kill you. But the gas chamber uses cyanide. When someone is executed in the gas chamber, it's potassium cyanide that is being used. And cyanide interferes with part of the mitochondria, and it stops a part of cellular respiration, so ATP is not produced. Hypoxemic hypoxia. This one always gives me a little bit of a chuckle because literally it translates into not enough oxygen, not enough oxygen. That basically says if there's not enough oxygen available, then there won't be enough oxygen available. This is suffocation. If something is preventing you from getting oxygen from the air, maybe you've got a pillow over your face, God forbid, or maybe you're in a small confined space and you've been breathing for a while and used up the oxygen. But whatever the reason is, if there's not enough oxygen available to breathe, then there will not be enough oxygen available in your blood to use. And the last one down here, carbon monoxide poisoning. And I included this with the types of hypoxia because it relates. Carbon monoxide, which is CO, not CO2, CO. Carbon monoxide is a molecule that likes hemoglobin more than any other gas. When carbon monoxide is available, it will bind with hemoglobin so that oxygen cannot. Carbon monoxide will bind to hemoglobin and prevent oxygen from binding. But worse than that, it's a pretty much irreversible bind. When carbon monoxide binds to hemoglobin, it stays bound to hemoglobin. And that means eventually all of the hemoglobin will have carbon monoxide bound to it, and oxygen cannot bind. And that's how carbon monoxide kills. Now, carbon monoxide is scary because it's colorless, you can't see it. It's odorless, you can't smell it. And its effects are that it makes you really, really tired, kind of irritable, and it gives you headaches. So think about that. You're tired, you're a little irritable, and you have headaches. Isn't that just normal life? So a lot of people that have carbon monoxide poisoning don't ever realize it, and they go to sleep and they wake up dead because they've had carbon monoxide poisoning without ever knowing it. That's why it's very important to have a carbon monoxide detector in your house. And if you ever feel like you may have carbon monoxide poisoning, you get to the hospital. But what do? Well, what they will do is put you in a hyperbaric chamber. They pressurize a chamber to raise the partial pressure of oxygen to the point that it's high enough that eventually it now will knock off carbon monoxide from the hemoglobin. Or if it is bad enough, they may just give a blood transfusion so that we can now have some oxygen binding to this new blood that does not have carbon monoxide attached to it. Carbon monoxide poisoning can be very, very scary since we don't even know we have it a lot of the time. Now moving away from oxygen and talking about carbon dioxide. Carbon dioxide is carried several ways in the blood. First, dissolved in the plasma. Remember, carbon dioxide is really soluble. About 7 to 10% of the carbon dioxide in your blood is dissolved in the plasma. Some carbon dioxide binds to hemoglobin, about 20%. of the carbon dioxide in your blood is bound to hemoglobin. Now, oxygen, remember, binds to the heme group, but carbon dioxide binds to the protein, to the globin part. And when carbon dioxide is bound to hemoglobin, we call that molecule carbaminohemoglobin, HbCO2, carbaminohemoglobin. And finally, carbon dioxide mostly is carried as the bicarbonate ion in plasma. So the bicarbonate ion, which we will see what that looks like here in a moment, is where 70% of the carbon dioxide in your blood is carried. Most of the carbon dioxide in your blood is carried in the bicarbonate ion in the plasma. So let's go ahead and switch over and draw how carbon dioxide is loaded and unloaded. Now this is going to be a very big picture. You will want a full page to draw this along, but we're going to draw it step by step so that it makes a lot more sense, and we're going to draw it as a very big picture. So I paused the video and made this drawing, and while you are drawing this out, I will explain what everything means here. But I didn't want to try to draw while I was talking. So first, the big red oval. This represents an erythrocyte. So as you can see here, this blue line, to the left of it is tissues, to the right of it is the blood. So over here we're looking at the blood, and this big red oval is an erythrocyte. The white board outside of the erythrocyte is the plasma. Now, in the plasma, remember, it's mostly water, so here's some water. But also inside the erythrocyte, there's water. There's water all over our body. Inside the erythrocyte, I've drawn two molecules of oxyhemoglobin. Now, the only reason that I've drawn two is because we're going to look at two different things that happen. There's lots of oxyhemoglobin here. Out here in the plasma, I've drawn a chloride ion, Cl-. Over in the tissues, I've drawn carbon dioxide and oxygen and shown that carbon dioxide, the pCO2 is high, the oxygen, the PO2 is low. And what we're going to look at is carbon dioxide loading. And we're also going to look at oxygen unloading. So earlier we drew what happens at the lungs and what happens at the tissues. We said that at the tissues, during internal respiration, which is really what we're drawing here, CO2 moved from the tissues into the blood. And we said that oxygen moves from the blood into the tissues. And now we've also talked about all the different ways that CO2 is carried in the blood and how oxygen is carried in the blood. We're going to tie all of that information together and look step by step how everything related to that happens at internal respiration. Now, oxygen, there's less going on with. Remember, oxygen was only carried two different ways. So let's go ahead and look at what happens to oxygen first. Some oxygen, remember, is dissolved in the plasma. There is more PO2 in the blood and lower PO2 in the tissues. So the oxygen that's dissolved in the plasma is going to diffuse down its partial pressure gradient from the blood, from the plasma, into the tissues. Now we also have oxygen attached to hemoglobin, oxyhemoglobin. Now, I'm going to draw something and I'm going to say something next, but then I'm going to come back and modify it when we see some other details. But for right now, we're just going to say the oxygen falls off or dissociates from the hemoglobin. And I'm going to write this a little bit backward from the way that we saw it on the slide. Instead of writing HB plus O2, I'm going to write the O2 first because of something that's coming later. Now you may be asking, why is it not HHB? We'll get to that, don't worry. Now the oxygen that breaks off from the hemoglobin is also going to diffuse into the tissue. So let me walk through that step again. Here the oxygen is attached to the hemoglobin, but that oxygen needs to get out into the tissues. So first it has to break off from the hemoglobin. That's what we see here. Oxygen and hemoglobin separate. The oxygen breaks off from the hemoglobin, and that oxygen diffuses out of the blood and into the tissue down its partial pressure gradient. So let that sink in. And now we're going to look at what happens to the carbon dioxide. If the oxygen isn't making sense yet, pause the video, maybe rewatch that part a couple of times before watching the CO2 part. So let's kind of step by step look at all of the different things that CO2 does. Some CO2 dissolves in the plasma, and CO2 is diffusing from high pressure in the tissue to low pressure in the blood. So some CO2 dissolves in the plasma. Now, remember, CO2 is really soluble, so when it moves into the blood, some of it dissolves right away. Some CO2 attaches to hemoglobin, so it diffuses into the blood, it diffuses into the erythrocyte, and meets with hemoglobin to make HbCO2, carbaminohemoglobin. I don't want to try and write that in this small space, but here is carbaminohemoglobin. Now, before we look at the other stuff that CO2 does, I want to go back to this oxygen that fell off. I said that what I originally said isn't really what happens. Let's look at what really happens. When CO2 comes in, remember, CO2 likes hemoglobin more than oxygen does. So CO2 binds to the hemoglobin that had an oxygen attached to it, and that is what knocks the oxygen off so that oxygen can diffuse out. So even though we drew the oxygen falling off of the hemoglobin first, that isn't what happened. The CO2 bound to the hemoglobin, which knocked the oxygen off so that oxygen was free to diffuse out. And then we're left with carbaminohemoglobin. But remember, most of the CO2, 70%, is found in the bicarbonate ion. So let's look at what that looks like. CO2 diffuses in to the blood, down its partial pressure gradient. It diffuses in to the erythrocyte, where it meets with water. Now here there's an enzyme called carbonic anhydrase. Carbonic anhydrase. And like all enzymes, it causes a reaction to happen quicker than it would on its own. And it does it without being changed by the reaction. This, the carbonic anhydrase, is why more CO2 follows this pathway, because the carbonic anhydrase causes this reaction to happen so fast. So carbonic anhydrase, what it does is it takes the CO2 and the water and it attaches them together to make H2CO3, carbonic acid. H2CO3, carbonic acid. Now, there's a lot of different definitions for acids. In biology, we only use a few of them. And the one that I use, I think, is the one that really, really best defines what makes something an acid. I say what makes something an acid is by looking at what it does when it is in water. When an acid is placed into water, such as this carbonic acid inside of an erythrocyte, it falls apart, it dissociates. And when an acid is placed in water, it always does the same thing. It falls apart and produces H plus and something with a negative charge. When an acid is placed in water, it falls apart, it dissociates. And the products are H plus and something with a negative charge. So this carbonic acid, it's an acid, it's in water, it dissociates, we get an H plus, but look back at the carbonic acid. If we take an H plus off of this, what are we left with? We're left with HCO3 minus. Take one H away, we're left with an H. We still have our CO3, but we also have a negative charge left over. So that's where that negative comes from. That doesn't mean 3 negatives. It means 3 oxygens and a negative charge. So HCO3 minus. This is called the bicarbonate ion. The bicarbonate ion. Remember we said that's where most CO2 is found? Well, that C and 2 of those O's came from a carbon dioxide. The H and this other H and the other oxygen came from the water. But the CO2 is hidden right there. Now, as we build up this bicarbonate ion and this H+, well, the buildup of the H+ is going to cause a problem. Every time a CO2 follows this pathway, we get an H+. And we've already said a lot of CO2 follows this pathway because of carbonic anhydrase. So a lot of H+ is building up. Why is that a problem? Because that's going to make this erythrocyte really acidic. And we don't want that. So we need something to resist pH change. What do we call something that resists pH change? A buffer. Are there any buffers in this erythrocyte? Think back to the very first lecture of the semester, or maybe the second. Hemoglobin is a buffer. So as H+ is building up, hemoglobin is going to do its job. H+ is going to attach to hemoglobin, and the result is deoxyhemoglobin, HHB. As H+ builds up, hemoglobin acts as a buffer. It binds that H+, and we get HHB, deoxyhemoglobin. So just like we saw with the carbon dioxide that attached to the hemoglobin, we're going to look at this H+ that attaches to the hemoglobin also, and we're going to say the exact same thing. Even though we drew the oxygen falling off first, that's not what happened. The H bound to the hemoglobin to make HHB, and that knocked off the oxygen so that it was free to diffuse out. We drew the oxygen falling off first, but really the H+ attached first, knocking the oxygen off so that it could diffuse out. And we're left with HHB, deoxyhemoglobin. But let's also look at what happens to this bicarbonate ion. Bicarbonate ion is building up and building up and building up in this erythrocyte so that it's got a really high concentration. A much lower concentration out here in the plasma, so the bicarbonate ion diffuses out. Remember we said most carbon dioxide is carried in the bicarbonate ion in the plasma? Well, that's how it got there. But that leads to another problem. We're taking negatives out of the cell. What does that do to that erythrocyte? It leaves it with a positive charge. It leaves it electrically charged, and that would not be a good thing. So we need to fix that. And the way that we do that is something called the chloride shift. Every time a bicarbonate ion leaves and takes a negative charge with it, a Cl- comes in and brings a negative charge with it. So we didn't lose or gain anything. That's called the chloride shift. And the function of the chloride shift is to maintain electrical neutrality or charge neutrality of the erythrocyte. The function of the chloride shift is to maintain electrical neutrality or charge neutrality of the erythrocyte. And there's one final thing that CO2 does. Well, we only said 3 on that previous slide, but there's really 4 things, and we'll see why we only wrote 3. Some CO2 comes into the blood, stays in the plasma, and instead of dissolving in the plasma, it combines with water. Now there's no carbonic anhydrase out here in the plasma, but that doesn't mean that the reaction doesn't happen. It just means that this reaction happens slower and not as often. Other than that, it's still the same reaction. CO2 plus water makes H2CO3, carbonic acid. What's plasma? Mostly water. So what does this carbonic acid do? It dissociates into H plus and HCO3 minus. Again, the result is bicarbonate ion in the plasma. So it's still part of that same third way where 70% of the carbon dioxide is. We say 70% of the carbon dioxide is found as the bicarbonate ion in the plasma. Well, that's the combined CO2 that followed this path through the erythrocyte and CO2 that followed this path through the plasma. If I were to just write a random bicarbonate ion, HCO3 minus, and ask you, where did this bicarbonate ion come from? Well, we don't know. Maybe it came this way. In all likelihood, it came this way because of carbonic anhydrase. But it just as likely could have come this way. We don't know. It's just in the end, 70% of the carbon dioxide is found as bicarbonate ion in the plasma. But we don't know which of these 2 paths it followed. All right, so I know that is a really big picture, and that picture is what's on page 874 of your textbook. But this is just carbon dioxide loading. What happens when we get to the lungs? We have to draw this entire picture over again to see carbon dioxide unloading. But rather than do that, I'm going to tell you the trick. When we get to the lungs, all we have to do is every single arrow points the opposite direction. It's the exact same picture, but every single arrow points the opposite direction at the lungs. So over here, instead of tissues, it would say lungs. The PCO2, the arrow would be pointing down because there's low carbon dioxide. The PO2, the arrow would be pointing up because there's high oxygen. All of these reaction arrows would point the other direction. Chloride diffuses out as bicarbonate ion diffuses in. As the bicarbonate ion builds up, then what happens? We're going to start to become more alkaline. So how do we fight off an alkaline? The buffer, hemoglobin, is going to let loose some H+, and the H+ will bind with HCO3- to form carbonic acid. Carbonic anhydrase acts as an enzyme to undo this reaction. It breaks carbonic acid into CO2 and water. The CO2 then diffuses out. CO2 that was dissolved here in the plasma diffuses out. This reaction happens in reverse, and CO2 diffuses out. As oxygen levels rise, as the partial pressure of oxygen goes up and the partial pressure of CO2 goes down in the erythrocyte, then oxygen is going to bind to the hemoglobin, knocking carbon dioxide off so that the CO2 can diffuse out. So everything on here that has an arrow, all you're going to do is erase the arrowhead and point it the other direction. Every bit of it. And that's how we unload carbon dioxide at the lungs and load oxygen into the blood. All right, so that is the end of this lecture. There's still going to be one more lecture for respiratory, and it is going to look at why we breathe. It's going to look at all of the chemical factors that go into causing us to breathe. All right, I will talk to you soon.